So these guys are going to follow today. Okay. So last week we left off by showing that Lpi is a contraction. Right. So others may leave if they want to. The guys who didn't actually revise last week's lecture, if you are so interested or so disinterested, you could leave. Right. So let's just teach for the 6 people who read. Okay, I don't care. Right. So there was one question last class to show that this actually works. We need to show that V is a Banach space. Okay, how hard is it to show that V is a Banach space? What is V? What is V? V, capital V. What is the space V we want to show as a Banach space? Space of all value functions. Okay. Well, value functions is a little tricky because value functions means that there is some policy or something that generates that, right? That need not necessarily be true. It's very hard to quantify such a space, right? So V is a space of all functions that satisfy something for us. What is that? Very, very simple. What is the most basic condition we put? Bounded, right? So component wise, the function is bounded. See, so if you think of an element here, right, and then I take V of S, which is one component of the vector V, right, that component will be always bounded, right. Okay, and think of what is the norm that we are considering here in this space. So essentially what capital V is, it's a space of all bounded what? Functions. Right, it's a space of all bounded functions, right. So because we have this function operating on a discrete space, right, so we can just think of this as points in space, right, but it's actually a function space, right, it's actually a space of functions, right. So capital V is a space of bounded functions, right, and what is the norm that we consider? Max norm, right, the max norm, right, and what is it that we need to show if it's a Banach space? It converges, right, but what we know here? All Cauchy sequences. What does a Cauchy sequence say? As you keep growing, difference becomes smaller and smaller and smaller. So what does that mean? It converges, it should be in the same space, right? So what can you tell me about any such space with a max norm on it? So it's a complete, it's a full space, right? I'm not excluding anything. Okay, the only problem I have is that my functions have to be component wise bounded, right? The functions have to be component wise bounded, right? And if you look at the, right, so essentially the idea is that since I am assuming that my functions are getting epsilon close to each other, my vectors are getting epsilon close to each other, and given the fact that they component wise they are all bounded, right, so the limit also has to be a bounded function, and as long as it's a bounded function it will exist in this space. Okay, so the easier thing to show is Rn is bounded under the Euclidean norm, right, under the max norm. So Rn is bounded under any norm. Okay, so the tricky part is this is not Rn, it's a subset of Rn, right. Why is it a subset of Rn? I'm just saying that all components have to be bounded, right. So Rn does not have that restriction. I could have some components that can grow unbounded, right. So the only tricky part here is show that, okay, since I'm talking about bounded vectors, okay, the point is the limit of this bounded vector should also be bounded. It's actually not always the case, right. I mean, I can actually set up situations where I am considering bounded entities, but the limit of the bounded entities happens to be, I can set up a sequence where I am considering only bounded entities, but the limit of the bounded entities happens to be something that is unbounded, right. But in this case I am not setting up any kind of a generic sequence like this, right. So I am actually setting up a sequence of bounded functions, so the sequence eventually has to be bounded. So it's a little tricky to show that, but the intuition is that it's going to be a set of a sequence of bounded functions, and I'm assuming that the difference between them is becoming smaller and smaller and so infinitely smaller, right, as it becomes larger and larger, and therefore you cannot have an unbounded value that is infinitely close to a bounded value. So therefore we assume that it's finally the limit exists in V. Okay. So I am not doing a formal proof for it because it involves introducing more concepts, but the intuition is there. So next we have to move on to the optimality equation, right. People agree with that? So you know the Bellman optimality equation. Oh, did I introduce all these notations? So we talked about this, right? Marginalizing over S prime. Did I introduce this notation in the last class? Right, so this is essentially the expected value of the reward given the state and the action, right. I am marginalizing over S prime, so essentially summing over the probability of seeing all possible S primes, and this we spoke about, right. So and yeah, so this is the optimality equation, right. So what we are doing to go from here to here, right, is writing this in a vector notation, right. So translating all of this into vector notations, if you remember I defined R pi as the expected value you will get following pi, right, for the next immediate step, right. So where yeah, so the only difference here is here I assume that you use a here, right, but here I am assuming you are using a pi, okay. And so this is the probability of the next state following policy pi, right. Here again I am assuming A, here I am assuming pi, and here I am saying V star j, and here I am saying V star. The summation is gone. Yeah.
Supposed to be V pi.
V pi. No. So I will tell you why, right. So I am doing max over A, right. So for each state I will get one max over A. So I will get one action as the max action, let us say, right. Let us assume that there is one action as the max action for each S, right. So what essentially does this give me? It gives me a mapping from state to an action. So what is that mapping? It is a policy. So that is a policy pi we are talking about here, right. This is essentially a component wise maximization of this expression. So for every state I will write out this expression, for every state I will find the A that correspondingly maximizes that expression. That is just like I did here, right. So every state I will solve this thing, I will find out what that A is, okay, and set that as the max pi, right. So this max here is a shortcut for saying it is a component wise max, right. For every S I will run this max independently. I could afford to do, I am not making any assumptions about the structure of the policy pi, right. So for every state I can set an arbitrary action as the action for pi, right. So this is my Bellman optimality equation written in vector form, okay, makes sense? Yes. So now I am going to define this as an operator, okay. So I am going to define L as that operator that takes in V star and does this computation okay, and gives you back another point in the space. Right, so L is an operator. So L is essentially, so LV and what we are claiming is that V star is the fixed point of L. Right, so last class we looked at Lpi, right, which was the iterative process for Bellman equation for V pi. Now this is a Bellman equation for V star. So I have written it like this, right, and then taken this whole operation and converted that into a single matrix operation, right, and so now the function essentially becomes LV is this. So L is a not a linear function of V, right, because of the max, right. So L is not a linear function of V. I'm just for convenience I'm writing it as LV. It looks like it's a matrix multiplication, right? It's not, okay, and that's basically it. And the claim here is that, what is the claim? L is a contraction. So if I say L is a contraction, what do you get? You get lots of things for free, right? So what do you get? If L is a contraction, we kind of hand wavingly argued that V is a Banach space. So L is a contraction. So what do you get? A. There is a unique fixed point V star, right? And if you do it iteratively, it converges to V star. Okay. So start from some arbitrary V, repeatedly apply L, it will converge to V star. So we got both these things for free. So let us look at showing this. Okay. Right. So when you say A star of S, it means that's the best action to do, at least one of the best actions to do in state S. You remember we talked about the grid world, you could go in any combination, so you could reach the top, right?
There is only one best action.
Not necessarily. Not necessarily. Right? So you could go either right or you could go up. I said any combination of right and up will work to get you to the final state, right? So either both right and up were the best actions. So it could be more than one best action. So both of these do not preclude multiple things being best. Okay, this is just finding out the value corresponding to the best action, right? So we argued that earlier also. There could be multiple best actions, but there will be only one value corresponding to those best actions. Regardless of whether you go up or you go right, you will take the same number of steps to reach the goal. Right? So the value will be the same, but you could have multiple policies. So I am not precluding this. Any one of those best A you plug in here. Right? Likewise, any one of the best pi's you plug in here and you compute V star. So I am not saying you have to find one pi or anything, right? So this here I am picking one such A. That is why I didn't say A is equal to A star is equal to argmax. I am saying A star belongs to argmax. Okay. So what we really have to establish is that later on, which will be useful for you when you are doing the assignment, is that you don't really have to consider probabilistic stochastic policies when you are doing when you are dealing with MDPs at least. You don't have to consider stochastic policies. For finite MDPs, there will always be a deterministic optimal policy. So it's enough if you only search for one deterministic policy. You don't have to search for stochastic policies. That we will have to show, right? What I will do is I will not do it in class. Okay. So I will give you a small write up to read. So from my notes I will make up a write up and put it online. So you can read it from Moodle. So just to convince you that. And it's a little bit of algebra, not too much, right? So just to convince you that deterministic policies are sufficient. Okay. But right now so far I have not assumed anything like that. I am just assuming there is one action that is the best, right. And let us assume that I have two functions v and u, okay, and I have L operating on v and L operating on u. Remember from our discussion in the last class that Lv is a function, Lv is a function, Lv of s is the s component of that function, or Lv acting on s, whatever is the output, okay. So the function is Lv. L is not operating on Vs. Okay, I think a lot of you had a confusion last class. L is not operating on V of s. L is something that takes a function as an argument and outputs a function, right. So Lv is the function, right. You take V, you apply L on it, and then the resulting function you apply on s, right. So likewise you take u, apply L on it, and the resulting function you apply on s, okay. So I am first making the assumption that Lv of s is greater than Lu of s, okay. So what do I need to show? It's come closer than Vs and Us, right. So that's basically what I have to. Remember we did this last class also, we did the same thing. So we assumed one way, we showed it, and then we flipped the other way, showed it, and then we showed that for every state yes, the absolute value in contracted, therefore the norm will also contract. Exactly the same thing that we did last class. That's why I asked people to revise from the last class and come, so that it will be, I can just go through this very easily, right. I am just clarifying this because last class, after the class, a lot of people were asking me questions about this Lv Lu business. So that's clear, right. So Lv is a function which is operating on s, okay. Right. So A star is the one that gives you the max, right. So that gives you the max here. So I removed the max and wrote it in terms of A star, right. So this is essentially L of V, okay. So I put a less than or equal to here. So I am going to do something on the other term which is L of U, okay. So if I am going to expand L of U, I might as well write equal to, right. So I am going to do something tricky with the other term. So what is the tricky thing that I am going to do? So what's the tricky thing I did? I got rid of the max here also, but instead of using the max corresponding to uj, I am using the max corresponding to v, right. So A star is what? It's the max when v is the function here, right. A star is the max and v is the function here, but I am plugging in A star itself here, right. So what can you tell me about this? It will be less than the actual max when L operates on U. You see that? So when L is operating on this, right, so essentially there is a max over here and there will be U here, right. But instead of taking the max action, I am taking some arbitrary action which is A star and I am plugging it in, therefore this will be less than the max, right. Therefore this difference will be greater than this, because in this term this is also the max corresponding to V, and this will be the max corresponding to U, right. So I am taking the difference, but now what I have done is I have replaced this term with something that's smaller, therefore this will be greater, this difference will be greater. Okay, is it clear? Huh? V is not optimal, but A star is optimal for V. But I am doing that maximizing thing here, right? So A star is the solution for this maximizing, this optimization. This is an optimization problem, right? So I am doing arg max over A. So A star is one of the solutions for solving this problem when the function here is V. It may or may not be the solution when the function is U. So if it is the solution, then this will be an equality. If it is not a solution, then this will be lesser than. Okay, great. So now the advantage of doing this, we can start cancelling out some terms and try to make this simpler. So what will you end up with is, so this term is equal to now this is the same trick that we did last time, right. So this is component wise difference, it will be bounded by the max difference, which is the norm, right, and once I write it as the norm, it becomes independent of J. So I can take that out and I have this summation, and this summation is 1, right. So what do I have here? So I have so I can do the same thing, I can flip things around, right. I can start with 0 less than or equal to LU minus LV, right, and then pick the action that maximizes the right hand side for U, and then do the whole thing, right. I will get exactly the same thing. So showing the other way around also, right. So I finally get that okay. So now this gives us a way of solving an MDP. How do I do that? Start with an arbitrary value function, just keep applying L repeatedly, I will end up with an optimal value function. So once I have an optimal value function, how will I recover an optimal policy?
Take the max.
I can do this. Essentially what I did here, run this on V star, right, this will give me an optimal policy, right. I can pick any action, any arbitrary action from that, from the argmax, and take that as my optimal action, or I could just define some kind of a probability distribution over that, take that as optimal action. Great. So we'll just write that down. So this is a very popular algorithm called value iteration, because you start with the value and then you iterate over it until you come to the final convergent value, right. So this is, yeah, so for people who are wondering about their programming assignment, herd management assignment, yeah, so value iteration is one of the things I am asking you to do, right. So you just start with an arbitrary value function, right, and then repeatedly implement L and run it till you come to a fixed point. The only interesting thing now here is what is the what? How many more times do I have to say arbitrary? What is the more interesting point? You talked about one end. I said it's not the right answer. When do I stop? Right? Yeah, not the number, but when do I stop? It can't be a simple number. I just can't say run 1,000 times. Okay. So I should have some other convergence test that tells me when it has stopped. Right. So essentially, I keep doing it until successive iterates or within. If they are same, you are great. I mean, but same will not happen. Same will take forever. Very close. That's
the same policy and the same value may not.
But then we are not computing the policy every time, right? The policy is itself a painful process. You have to be greedy with respect to the value function. So every time, if every iteration you are computing the same policy, it becomes a problem, right? If you are going to compute the policy in every iteration, then it might be a problem because you have to do an additional computation. Maybe not. I mean, it's a call that you have to make. But if you want to give certain guarantees about what will hold when things converge, then you better have a bound on the value function. Okay. So we will come to another algorithm called policy iteration, where we can work with the space of policies. Okay. But right now I am just going to do this with value functions. Right. So select some V naught belonging to V. Pick an epsilon for our stopping criterion and start your iteration. There is nothing. I mean, just I've written it component wise. I've written your Vn plus 1 equal Vn plus 1 equal Lvn. That's basically what I'm asking you to do here, right? So this is nothing. Okay. So the interesting part is this. This is fine, all of this is fine. The only tricky thing is, why do you have this weird expression here? Why not just epsilon? Why do you have epsilon into 1 minus gamma by 2 gamma? So I am doing value iteration. What am I computing? No, what I am interested in, what do I expect to output at the end of
And after
huh? V star or pi star or whatever, right? I am expecting to output V star, right? But my stopping condition is on Vn and Vn plus 1, right? But I would like to give you guarantees on how far away I am from V star at the end of the day, not necessarily how close Vn and Vn plus 1 are, right? So we will take this closeness condition and convert it into a guarantee on how close you are to V star, right? And then when we do that conversion, we will find that you will be, what do you think you will be? Guess, guys, I mean you should be able to guess by now. What do you think we will be? Epsilon close to V star. Okay.